Yeah, I just need to plug in.
Okay, your moment of inertia, turn them into numbers, like point something, something, okay? And that way you can compare them.
Oh, like a ratio, right?
Well, let me think about it in terms of what we know in class. What does 0.66 mean for a moment of inertia?
0.66 is 2/3. Right, so
What does that mean?
that means that, like less different.
Right. What was the extreme that we used? Yeah, we had two cases, right? Had a case where like it was undifferentiated. We said that was 2/5.
Right. Oh, in this scenario, it's like saying that. That the original was less differentiated, or excuse me, was more differentiated, and then the new mass is less differentiated.
Right.
Is that what you'd like us to write down as well?
Yeah, words. Anyone can do it. You're a physicist.
Right.
Yeah. So you want to interpret it. So I like a little bit of stuff at the end saying, oh, this makes sense. I'm confident this is the right answer. Right? If I ask you for how many Earth masses, right?
Right.
Then I want you to be like, oh, it was surprising. Or it wasn't surprising, right? Okay, now 40% of the class is here. We can start. I did not have enough time to put all the slides together properly, so we are going to be winging it. So I owe you some surface of the Venus, and you won't get that today. Sorry.
It's okay, you won't get what's verbal, it's favorite.
It's okay. So we were looking at the altitude maps and emission. So the hotter places were the lower places, right? And we're going to talk about the surface of Venus just for a couple more minutes, and then we'll compare it to Earth's surface and Mars's surface. And then once we're done with surfaces, we're going to immediately get into atmospheres. And atmospheres will take a little bit more of our time because we'll have to talk about dynamics, we'll have to talk about heating. How do you heat a fluid, right? Okay. There we go.
There we are.
At the party now. Why is it not working? Why is my thing so angry to me? What? Ma'am?
Need someone to sit there and look at and say so.
Yeah. Next slide. Okay. So radar maps of the surface of Venus, like this one from Magellan, show volcanism in a lot of detail, or features that are consistent with volcanism. Let's remember what radar reflectivity means. Smoothness. Smoothness. So how do I interpret this picture here? Is this a large white plane? No, what is it? Yeah, but what about this white plane area? Smooth. Wide, smooth region. Do you see craters in this image?
No, well, not in the.
Not in the smooth area, right? That's new surface. Okay. So there's features that look like tectonics-ish, but of course we'll see that they're not. We'll see deep troughs that resemble subduction zones, and large ridges that resemble mid-ocean ridges. And you all went and looked up what a mid-ocean ridge was, right? Yeah. What is a mid-ocean ridge? Go ahead, do the hands. On the side of the ocean? Okay, this is a crust thing. Okay. Here's my crust. Here's my magma. Hot rises. Okay. Then it gets to the top and it has nowhere to go because there's a lid. So it goes over to the left, to the right. And in the places where it diverges, it pulls the earth.
Isn't where like the new crust is forming?
Right. And so magma bubbles up to the surface here. Now there's some water, not to scale. And you get a nice little crack in the ocean. This crust goes on to hit some other big continental crust and squish into it. That's either a subduction zone, if it goes below, right? Or it gets uplifted, right? Gets compressed sometimes. Okay, so this seafloor ridge is evidence, in our case, on Earth, plate tectonics, new crust is being formed, being pulled apart. Here, these things look like mid-ocean ridges. Long places. You see this rill here? Right? Long places where crust is being apparently constructed. Right? And some large shield volcanoes. So you have things like pancake domes that are unique to Venus and really runny flows. So lava flows that are just very emblematic of, say, Hawaiian viscosity of magma. This material is going out onto the surface in all directions. It's flowing on the surface like this. The only liquid in town. It is. Good. Not very many impact craters. What's the surface age of Venus? Yeah, how many? Even?
Couple hundred million.
Couple 100 million? How many 100 million? About 600 mils. Okay. A lot of this activity is extinct. Doesn't look like there's been much tectonic activity within the past few 100 million years. So it's dormant on time scales that are smaller than the age of a tree. Okay, so geologically speaking, depending on how you want to think about that, that could either be considered new or old. Okay. There are active volcanoes. There's just not a lot of them. There's also not a lot of craters. Total. There's no piece of the Venusian surface that's older than 700 million. Not one. How and why? Excuse me? Well, it's not active for the last 100 million years, right? 200 million years. Good. What do we think? How can all of the crust disappear? What? There doesn't appear to be any sort of plates. So there doesn't appear to be any subduction zones. They look similar to subduction zones in the compression regions, but there's no evidence that we found for crust recycle. Did I talk about this? Hold on. Okay, let's go back in 1 second. So I didn't put this in slides, but this is Fairly common belief system about Venus. Inside, hot. Right? Outside, cold. Right? What do you form right here? Crust. Very good. What's that? Dried out, cold. So let's imagine there's no atmosphere. So this is the crust. And it's the coldest part of the planet, right? Because it's touching space. How does it get rid of heat? Yeah. What physical process allows the crust to remove heat from itself? Volcanism gets rid of heat below the surface, right? By what process? Radiation. Okay, so photons come off. In fact, you just calculated black body temperatures, right? What?
It emits the
It emits heat, right? Heat radiation. So radiation is the only way to cool it. Radiative cooling. Okay, that's a loss. Net loss. Okay, so these rocks here, they are crystallized. They are rocks in the conventional sense of the word rock. Down here, okay, you have some mixture of liquid and liquid solid magma. Why? Because it's hot and it's under a tremendous amount of pressure, right? Okay. So let's imagine the surface is not heated by anything, and we just have an object that's hot in the middle. Let it sit there. Which direction does the crust move? This way or that way? Inwards, towards the vent. The crust will grow as it cools, right? So this is, I want to say maybe 200 degrees. T equals 300 Kelvin. That's well below the freezing point of rock, right? And so the temperature for condensation of T equals 1500, right? That begins to move inwards as you lose heat, okay? Okay, but now we have a problem. What's the problem?
As it moves inward, it'll melt.
What?
As it moves inward, it'll melt.
Yeah, so this moves inward, so you get a nice thick crust. Good thick crust. Okay. Why does it start heating up again? Well, so this thing is producing the heat, right? How do you get rid of heat in here? No, in the interior. Inside, how do you move heat from the core to the outer parts? Convection. So here I make hot go up, it cools, and then it falls back down. Those are convective cells. That's an efficient way of moving heat from the center. Is radiation as efficient as convection? No. Because if you step into an oven, right, you can put your hand in there, and you're most likely to be hurt by the fact that the air is warm than the fact that there's light coming off your hand. Now you shouldn't do either one. But this convective heating, this radiative heating is less efficient than convection. So you can have a situation where this thing grows, and now there's no ability for heat to get out. And this temperature difference in here rapidly increases. And suddenly the whole crust catastrophically melts. Because convection is still going on, it's getting a lot of heat from here. There's no way for the heat to get out efficiently. And suddenly you go from a situation where the crust is moving inwards, 1500 degrees, and then it rapidly rebounds in order to let that heat out. And then, then it melts the whole thing again. The whole thing becomes magma all at once. And then it starts to cool again from the outside. You see? This is called catastrophic overturn. All right. What's the scientific problem with this? I present to you a hypothesis for why the surface is at maximum 700 million years old. What have I created unknowingly? Or maybe knowing. Yeah, I got rid of the surface. Surface is gone. Yeah, so there's no evidence of anything above 750. Right? So I have no ability to test whether this is correct. Plate tectonics, at least, I can go and look at very old rock and say, oh, this old rock used to be friends with this old rock. They're the same rock. And they split apart 100 million years ago. Right? I can show that they were evidentially connected. This one here, how do you test? Are we're gonna wait 600 million years? We don't know how long it takes to catastrophically overturn again, right? We don't know if it ever will. You see? So this is a working hypothesis that has a lot of issues. Now, does this mean it's not scientific? No, because we can create models that are based on physics and say in which conditions does this occur versus not occur. It is certainly observable that the entire crust is gone 700 million years ago. So needing to explain that is a scientific endeavor. But what you need to do now is when you have those models in hand, you can make arguments about what the composition of the surface should be because of that catastrophic overturn. Does that introduce volatiles? Does that get rid of specific minerals? Right? What can you predict about the crust based on that model that would be different than just volcanism for 700 years, right? 700 years. You see? Okay. Okay, so that's fun. Venus is fun, right? And we have some other batshit crazy ideas for Venus, but I'll talk about it. Here's the crust. You can see that it has these really fun ripples in it, like fissures. Those are cooling. So you start something very hot. Think about bread, right? It heats and it expands, and then it cools when you get in the surface, or cracks, right? So that's why if you have a nice sourdough, you cut a line, but can let out that steam as it cooks. Okay, that's the surface of Venus, but no one cut nice lines in it. Okay. Okay, so like Earth and like Mercury and the Earth, Venus is certainly differentiated. It's got a bulk density that we mentioned is large. It's about 5.2 grams per cubic centimeter. It's got mafic silicate rocks, and you can see that from the landers. But the moment of inertia here is a third. So you're all experts at moment of inertia. What is a third moment of inertia?
Let's differentiate.
A third? Less differentiated than what?
And 40%. We're talking about between 0.3 and 0.4 since differentiating 0.4.
Okay, so let's ask this question again. What does this number mean in front of the MR squared? Good. How differentiated it is? Are bigger or smaller numbers representative of more or less differentiation? Bigger or less? Why do you say that? Let's draw some examples. Here's a case study. Okay, here's my planet, radius r. and all of the mass is in this ring around the exterior. Here's another one. Undifferentiated, where rho is constant. And you just calculated one, didn't you? Here's one where rho goes like 1 minus r over r.
Six hundred and 24 times or 125, that's the constant.
What was the formula for the original density? What? Original density. What was the original density? It was uniform. So this one. What was the original? 2/5 or 0.4. That's uniform density. Okay. What about this one? What we did in class? More differentiating. Most of the mass here. Less mass out here. Less mass out here. Yes, do we know? We did 2/3 in class as well. But it's this one.
Was that the 2
Right. Lower means more differentiated. Now I hate these numbers. So I'm not going to use them, and you shouldn't hand me something that's 6,000 over 8,000. Okay, I will just throw it back to you. It's not a number that anyone likes. You don't know what that means. You don't have an intuition. But this you do. 0.6 and 0.4 are very easy to interpret. Which one's bigger? Which one's less differentiated? 0.6. So if I tell you that we measured Venus's moment of inertia and we found that it was 0.3, what does that tell you? It's well differentiated. It's always with respect to something, right? We can't just say things. We have to be very, very specific. Now we're not just talking about neutro-astro. We're talking about data. We're talking about, right? We want to make a comparison. We want to be quantitative. So you're right that it's differentiated 100%. But how do I characterize that word well?
It's more differentiated compared to the uniform density.
Compared to uniform density, it's more differentiated. Right? Is it more or less differentiated compared to the one that we did in class? See? That makes sense? Cool. This is how we talk. You would suspect that Venus's internal structure is similar to Earth's. Why would you suspect that? No, no, no. You would suspect that the internal structure of Venus is similar to the Earth. Why would you suspect that? Similar radius and mass, yeah, same size, right? Same size, probably same neighborhood, probably made of the same shit, same solar, right? Why would it be different? Right? Yeah, a little closer, but does distance have a big effect on the interior? You think yeah? How? What's the mechanism? How do you get the information from outside into the core to change the composition of the structure?
Because it's well, the first thing that comes to my mind is the gravity. As the gravity, if you're that close to the sun, then you get probably more stuff than.
Okay, okay. I like the idea, but we're forgetting the scale. This is really important. If you think about the Earth, and you think about the distance from the Earth to the sun, how many Earths can you fit in between the Earth and the sun? Yes, order of magnitude, 10, 20, 10, 100, 1,000, 10,000, million. We go on 5,000. 5,000? 7,000?
30,000.
30,000? 2,000. It's about 23,000. Okay. Venus is 70% of that, roughly the same size, 70% of 23. Okay. That's not that much closer. You're thinking about Mercury, which is going to have strong pull, right? Because it's real dang close. Right? And then you're going to have issues with flexing, like we saw with the moon. But at Venus's distance, we don't expect it to be very different. Okay. So we think that you have a liquid iron nickel core. When I say the word plastic here, I do not mean plastic that you make stuff with. I mean that it moves with plasticity. Okay, and a crust. The crust is not plastic, it's hard. The mantle is that weird liquid mixture interior and liquid iron nickel core. And we think that it looks very similar to the Earth, except for the crust looks like shit. Okay. And we suspect that Venus's original ingredients were similar to solar system bodies. What do we mean by that? We will see in this class that we will study remnants of the early solar system, the stuff that did not make it into planets. These tend to be the oldest things we find. Why? Because they're never remelted from when they first formed. Okay? They come out of the disk, they're just elements, they start to condense, and as they condense, they form minerals. And those minerals never melt. So great, they hold the age of the universe. They hold the age of the solar system. But if you incorporate one of those rocks, that is to say, you put it into the Earth, even if you found that rock later, what is the melting age? Whenever it melted, right? Whenever it joined Earth. Because you're not surviving a lot of cases, right? Sometimes you get little meteorites and they fall to the Earth, and those are great. That's how we study like the Martian rocks, for example. Martian meteorites. But when we look out and we see meteorites, we look in sort of the local area. There are rocks in the asteroid belt. There are rocks that are in between us and Mars and us and Venus. They don't always live there. They get farther, they get closer, they go back, right? This material probably, we think, made us. Okay. So we suspect small solar system bodies had lots of organic minerals, molecules, and ices. Okay. And this is where they think a lot of the carbon, nitrogen, and hydrogen comes from in meteorites. Liquid oxygen. Okay. So here's the issue. When Venus was born, as you just showed in your homework, you have a molten surface. Whole thing's melted. How are you going to have an ocean when the whole surface is 1400 degrees Kelvin? Real hard, right? Good. So what we think is probably these evaporate into a temporary atmosphere. And you have a significant amount of loss. Ultraviolet light from the sun comes in, breaks apart, say something like water into H and O. And then each one of those can escape separately if they need to, right? Specifically H, which goes very easily. O can do that, but it's hard. Okay. So, when you look at something like Venus, and you look at something like the Earth, it's actually poor in carbon, nitrogen, and hydrogen compared to the meteorites that we look at. And, in particular, compared to the sun, from which we're made. So here it is. Here's the Earth. Here's the Earth. Here's the sun. Look at a lot. It's most of that. And then we're going to look at the solar abundance of that. And then comets. Okay. And we're looking at these numbers are per 100 atoms. Okay. So let's have a look at the first one here. Here's carbon. Per 100 atoms, it's less than 0.1. Whereas the sun and comets share. Right? I mean, these numbers are basically identical, right? Hydrogen is really the only difference. Excuse me?
So that's pretty simple.
Yeah, phosphorus is, yeah, that's very good. Right? That's pretty wild. Look at us. Okay, not a lot of carbon. Similar oxygen. Okay. That's your yeah. Perfect. That's your reference atom here. Good. We have more magnesium than the sun. Is that surprising?
No.
Why?
So the sun's mostly composed of hydrogen and helium.
Good, but per 100 atoms, why is it not surprising that we have magnesium and silicon and iron? You think they'd be the same, right? What are we made of? Not we, like us. Yeah, what is the Earth made of?
So
Look at that. Primary building block. Silicon, magnesium, and iron, right? Didn't we say that we're like rocky? Something like 4 or 5 grams per cubic centimeter as a whole. Okay. There's our building blocks right there. And when you grab something like this and add it to that, or add this to that, that's when you get a rock. So in fact, you can condense these rocks, silicon with oxygen, in the disk and add them to the planet. And you think to yourself, okay, good, per 100 atoms, this is perfectly fine. But then you have to have a loss process to get rid of the rest of the 100 atoms so that you appear to have way more iron than was provided to you. If you kept all of the original elements that you started with, then this number could not be larger than 1.2. You have to lose other things in order to have most of your atoms be iron, right? Okay. So let's have a look at where we lost it. Carbon's gone, hydrogen's gone, nitrogen's gone. Right, these are the sun elements that are the most abundant. We have like none of them. Right? Okay. Does that make sense? And these trace elements, we got a shit ton. So I asked this question in my Astra 1000 class when we get to star or to planet building. You crank up the trace elements in the early disk. What kind of terrestrial planets do you build? Yeah, crank up everything from oxygen down. Sodium, magnesium, all these numbers, make them larger. How would you get less structure? Let's assume we know nothing about how gas transform. Let's say we crank up the production of all of these, we make more. If you produce more of these objects, you will get larger terrestrial planets. So if you think about the history of solar systems within the universe, the very first stars converted hydrogen to helium and then helium to carbon, nitrogen, and oxygen, and so on and so forth. And it would take a whole generation of stars exploding and dying to put that material into the universe again, from which new stars could form. So the very first planets likely were not terrestrial. They were gas giants, right? They had to be gas giants. There was no material from which to form silicon, magnesium, or iron, right? Okay, so now we keep waiting. Let's wait 10 billion years, 30 billion years. Your expectation for terrestrial planets is that they should be larger planet, right? Make sense? Okay. Okay, so that tells us about the abundance of these rocky type things, the stuff that we make rocks with. But we have hydrogen, carbon, nitrogen, and oxygen on the surface. We're breathing some in currently, and so we have to go back to this age-old question that scientists have been asking for generations, which is, where did you get the water that you're drinking? Is that water or blood? Where do you come from? Sports. That's correct, but I don't like the answer because it's too far back. Where did it come from in the solar system? Because I just told you that the addition of all of the material that we originally added, all of the volatiles, they evaporated right away because the surface could not support a liquid ocean. Okay? And once the surface cooled and melted, now there is an ocean. That seems like a contradiction. Gassing is one way to get material from the interior where they can be trapped and not evaporate, start to build an atmosphere. And comets are volatile rich, right? Those are certainly acceptable answers. There's also probably hydrated asteroids in the outer main belt. Folks are looking at the ratio of deuterium to hydrogen. Of course, water can accept either one. So D to H is a good metric of basically the age of that object. Specific populations have different D to H ratios. Okay. And you can look in the solar system as a whole. Comets D to H ratio is not quite right for Earth's water. Asteroids, the close ones to us, don't have enough water, but the D to H ratio is right. And the far asteroids, the ones closest to Jupiter, appear to have sort of that in between. And of course, the likely story is that it's a combination of all of them, right? That there's some outgassing and some fraction, there's some fraction of cometary delivery, and there's some fraction from the asteroids. And then that makes the D to H we observe in the ocean. Okay. Oh yeah, there it is. 90% from asteroids, 10% from comets. Okay. Okay. Wow, that was good. That was only 40 minutes on 3 slides. So maybe we won't get as far as I thought. Let's talk about Earth as a planet. There she is. Birdie. No disgusting violence that Venus has. Venus is beautiful from afar. Right? Venus is like the rose bush that you have picture in.
Destination.
Destination?
It's not a destination.
Oh, not a destination. Yeah, not this. It looks better in the picture. Right? Okay. We're not going to talk about this. We're not going to talk about that. We're not going to talk about. We'll talk a little bit about geology. No, we're not talking about that. We'll talk about that later. We're going to talk about plate tectonics and we'll talk about the core. And then we're going to jump right into Mars. And then we'll go into atmospheres for all the planets. Okay. Questions? Is this to scale?
No, it's very close to scale.
Yes, that's
Slight difference.
Which one's what?
Venus or say this one.
What do you look at? What's that object right there? What's the landmass? Very good. What's this? Yeah. This right here. That's the Suez Canal. And that's where everyone got stuck. You know everyone? The giant shipping container that got stuck in the Suez Canal and stopped shipping during the pandemic. All right, here's Earth. It's big. The mass of Earth is 1 Earth masses. The equatorial radius is 1 equatorial Earth radius. That's pretty good. Average density. Does that mean? Nathan, yeah. Nathan, right? Okay. Moment of inertia. More differentiated than uniform density. That's the right way to talk about, right? Okay. Less differentiated than what? The example you did in class, right? Not the one you did in your homework. Right. Okay. More or less differentiated than Venus. Same that. Good question. Okay. Albedo.
Not too high.
Not too high, right? Why is that?
It's blue.
Because blue. That's big blue dot. Right? And that's in dark. Right? Does the albedo of the Earth ever change? Yes. That's when. Two. There's 3 different answers. There are future, and there's not that, and it's seasons. Okay. Ice ages. Weather. Good. Doing all right. Seasons work in which season was this happening? Where's most of the land on
The southern hemisphere. Like northern.
northern? Does the ocean's albedo change? Not frequent. So very infrequent. The clouds do, but generally speaking, the ocean itself won't change as much. But the land changes dramatically, right? The land goes from green, which is literally designed to absorb light, to brown, which is very, very light, or in some cases, white. Right? So that can be the largest shift in albedo. Now, of course, clouds exist too, but clouds, as we'll see later, they can have 2 different effects depending on their altitude. High altitude clouds trap radiation in to keep the planet. Low altitude clouds maybe can block it or bounce it before it gets absorbed. What? Oh, be weird. Yeah, no one wants that. Oh, and I just said that. That's the opposite of what I meant. Low altitude clouds trap it in the blanket. High altitude clouds bounce it before it gets absorbed. My brain. Okay. Effective temperature. Cold, right? Now that's effective temperature. What does that mean? Effective temperature? It changes. What? I would say average temperature and then average temperature. Effective temperature has a specific word, specific definition. I think you're thinking of the word effect, like this is the effect of that. This is the effective temperature, which would mean the effective temperature would be as if it were a black body.
Are you telling me like this is an order?
That's it. So we call the effective temperature, which ignores any source of greenhouse gases or atmosphere. That's your effective temperature. Is this the temperature on the Earth? Well, fuck no, right? Because otherwise what would happen? We'd all be frozen tundra babies, right? Okay. So this is what we compare to when you think about distance from the sun, how much radiation we're getting, etc. Okay, so the effective temperature is quite low, and in the absence of some greenhouse effect, we all die. Good. Does that ever happen? In the absence of some greenhouse effect. I see. Yeah, never mind. Cool. All right, something major axis. It's not actually one. So that's straight as that is. It's actually 1.000011. But that is what happens when you define things without knowing how precise you can define them. The orbital eccentricity is about 1.5%. So if you show the two pictures of one with eccentricity of the Earth and one with the circle, you would not get this. Notice what we said last time? Sidereal revolution period. We're talking about Venus, for example. What does that thing mean? Shows the same face of the sun. Shows the same face of the sun. And it's not quite 365, right? It's 365 and change. And so we have to make up for that with leap years and leap days. So this year, did we have a leap year?
Yes. So on here.
Yeah, I think we did.
Did we?
Yeah, or yes. Yeah, February.
Okay. When do we not have?
Everybody.
Every
400 years? And there's two rules actually. All right, you can look those up later. It's very stupid. Okay, and this one's here, my favorite one. Here's the length of the day, right? 24 hours. What's this?
Say here.
Same place in Earth, right? So the same face for the sun, right? As opposed to the length of the day, which is 1 4. Okay. Okay, it has a strong magnetic field. Big magnetic field, boy. So what does that tell you about the interior? It's hot. Now, even if you didn't know, right? Even if you didn't see pictures of Hawaii or seafloor ridges, right? You would know it's hot because there's a magnetic field. There is a magnetic field and it's strong. That's basically unequivocal evidence of a dynamo. Because as soon as you run out of some of the components for making a dynamo, your magnetic field strength goes way down. Right? Magnetic fields are the rubber bands of physics. What I mean by that is they do not want to be bent, they do not want to be distorted. So you create them, and in the case of permanent magnets, they stick around for a long time. But if you're generating one, and the thing that stops generating it finishes, you're almost immediately turning it off. All right, here's your plates. Mercury was differentiated, Venus is differentiated, the Earth is differentiated. It likely has an asthenosphere, which is just a fun way to say the mantle, a lithosphere, which is rock sphere, my favorite word ever, is the crust. So the eating the crust is the best part of the pizza, and that's where we live. These are the plates from whenever this was taken in the geologic survey. You'll notice that the Eurasian plate is Mondo. Pretty important plate. Right. North American plate, there's some arguments about where the plate definitions are. We think the Eurasian plate is probably very accurate. The North American plate has some issues. This is your seafloor, all the way through. This is that line that splits this continental crust here from this continental crust here, and you notice how it goes, and it goes, right? That's what they used to be brothers. They used to be together. Split. You can see that. What's that like? Okay. This is the location of the plate boundary. The Nazca plate is going under the South American plate. That creates the Andes here. And the Rockies are here. This is the closest plate. This is the one that we live on in LA. And we're going to go join Alaska. You can see this is Hawaii, and then the Emperor Seamounts go this way, and then this way. That's because the plate was moving like this, and then it turned like that. Over the. Okay. So everything's hitting each other. The Antarctic plate is doing who the fuck knows? Okay. Living his best life, no one interrupting it. They float on top of the mantle. So the way that you need to think about class, of course, is that it's like a boat on the top of lava. If you stand and you look down, you're just looking at lava, right? Some of the plates are denser, and this is the basic reason why you have subduction. Generally speaking, if you have an intersection between continental crust and oceanic crust it's denser and will subduct, go under, to be recycled. Continental crust, when faced with oceanic crust, very likely to go under because it's lighter. Right? Just take two things, two different fluids, press them together. Which one goes over which? Okay. Okay. The denser material are generated from the mantle at these mid-ocean ridges that I just told you about. And this makes the ocean floor. Some ocean floor, right? So for example, we talked about sedimentary rock creation. What's an example of a sedimentary rock? In the ocean? Very close, yeah. Limestone, sandstone, right? Yeah. I was thinking about limestone, sandstone works for a sedimentary rock. But those are rocks that are formed on top of our oceanic crust. Right? Crust itself and the rocks that comprise it will be made of different things, right? And at this boundary here, where the material is coming out, that is not sedimentary rock. What is it? Lava comes to the surface, it becomes what? Magma, or what kind of rock? Use lots of different words here. Black rock, yeah. Volcanic rock is where I would start. Minimum, I would call it volcanic rock, like basalts, right? Something like that. You might call it, say, a plutonic rock because it comes from Hades, right? Pluto, the underworld, right? You might say it's extrusive, it's coming out. Okay? Minimum, call them volcanic rocks. Okay. All right, so that's forming here at nothing. And then you layer some shit on top of it over millions of years. And it lives its sad little fucking life. Whatever. Okay, this whole life. And then it, just keeps living. So this stuff here is super old. There's no reason for it to not live its life. And then this stuff is like, wait, what the heck? I lived this whole time, and then it gets crushed by this other plate. It's destroyed. All right. Let's see another place where you generate crust. Let's see. Okay, so this thing is being split in half. This is continental crust, and it's actually diverging like this. There's a nice little rift valley here. Rifts are just where a bunch of lakes exist. Rift is opening up. You're getting new material there. Okay. So I spent a lot of time with that. That's fun. Okay. I hope this works. This doesn't play on the sound. So this plate tectonic system we think is unique. It's there's tectonic activity on Venus. Certainly, we see the compression. We see like these straight long ridges where we think potentially you have new material coming out from below the crust. But I don't know that you can assign plates in the same way. Cool thing about the Earth when you look at plate systems, let's go back one. All right. So if you look at the distribution, and maybe I'll show that in the next class. Look at the distribution of volcanoes in the Pacific. Okay, so you have volcanoes here. And then in general, you have no other volcanoes except for on the rim at the lake. So, like, how we kind of think about and define lake boundaries. And so this ring of fire that this region is called, of course, you have very explosive volcanoes up here and all in this region. That's all from the regions right below the cross. Venus, we don't think has anything that resembles that, but of course we don't know. We don't have seismometers on the planets. Nothing will survive. Okay. This better work. God damn it. Okay, well, I'll get that video to work next time. It's pretty cool. You know, it shows that we had an NGA and shit like that. We love these felsic minerals. What is felsic meaning? Iron rich, right? So they, surprisingly, felsic minerals float. The iron rich minerals are the floating ones. And those are the ships that carry us. Okay. Which one's heavier? Just to clarify for 1 second. Water or continental or oceanic crust? Yeah, which one floats better? Continental crust floats better than oceanic crust, right? Good. What is lighter? Water or oceanic crust? Water. Right? The water should be above the ocean. Okay, good. Why is the water only found over the oceanic crust? Go back a second. Why is the water only found over oceanic crust? No, on top of water. Well, we don't have, like, here, you don't have a mixture, right? This is one plate. This is essentially one piece of rock. Over here, you can think of continental crust as ice, right? You can think of this as a different, denser version of ice. Which of those two things sticks out of the water? The ice or the denser ice? The ice does, right? Because if it was the same density of water, it would sit in the water. Okay, so this is how you think. You have some piece of ice with a little peak standing out. You have another piece of ice, which is still frozen, but more dense. And so necessarily when they both sit on the water, the lowest point is the more dense frozen ice. Okay, and so the water just pools to the lowest point. There, of course, are exceptions, right? There's water in here in Lake Baikal, which is on top of continental crust, and these whole regions here, which hold a great fraction of the world's freshwater, are of course. But it's nothing in comparison to oceanic water, right? C'est bon? Okay, whew, that was a lot just talking about some colors. Let's talk really briefly about the Earth's magnetic field. Magnetic fields are dope and also very weird. So you need to have differential rotation. You need to have the interior rotating faster. Okay. So, you know, people who do this, like Gary Glatzmeyer at UC Santa Cruz, builds geomagnetic models of the interior and was able to show how you make a dynamo. He was the first person to do it. It's really fun, really interesting stuff. But you need to the effects of things like pressure, temperature, the fact that the density can change, the fact that it can give away its heat, and then what state of matter is it? Because is it conducting? Is it non-conducting? Right, keep track of all of these elements. But what they find, of course, is that you have a metal iron core that's super rotating, something that's conductive, that has free electrons, and is rotating faster than something next to it. You can have shear. And that shear creates the dynamo. So this thing is, the Earth is spinning, right? Why does the Earth spin? Shit. Fuck, that was a hard one. All right, why does the Earth spin, folks? Yeah.
Bro, I heard way back in middle school, was it because of its impact, just the rotate?
Everything spins. Not everything was necessarily hit. Yeah.
Rotational energy.
Okay, let's say that a different way. There certainly was rotational energy. I'm going to just change one word there. Say rotational angular momentum. Right? So all the stuff started very far away, and then it contracted like a I stands for I stands for, correct, right? I stands for ballerina, right? And you spin fast. So everything started spinning because it started off far away, and by the time that it became small, now it has a lot of angular momentum that's conserved, and now you're spinning quickly. Okay. But it's not spinning uniformly. The interior is spinning faster than the exterior. Is that fucking weird or what? Right? The interior, the core, is moving faster. Is that surprising? Why is it surprising?
Would that be distributed on the outside?
What?
You said the interior is getting faster.
Yep.
Yeah. Should it be on the outside?
Well, think about it this way. Let's say you had a bunch of concentric, like circles with ball bearings in between them. Okay, you spin the whole thing together, right? If you spin the whole thing together, you expect all the rings to move together. But if they were flexible somehow, as they rotated in, you take all that mass and you bring it in, what happens? You go faster. The core, by definition, is going to be spinning faster because it's the most mass, and it's got the most angular momentum. And every time that you have this circulation, right? Let's say you bring heat up, you're depositing, you're differentiating, you're bringing down more mass, right? So you're increasing the angular momentum of the interior at the expense of the angular momentum of the exterior. Is the Earth's surface going to slow down? Now, this is complicated, right? Because you're thinking, well, if it freezes, then of course you'd be in solid body rotation, right? But is it going to slow down before angular momentum is spent? In fact, the Earth is slowing down. It has been slowing down for a while. Why? This is a red herring based on our discussion. This is using information that we've learned 4 weeks ago. So the moon is slowing us down. The moon and us are exchanging angular momentum, and the moon is receding. As the moon recedes, it is due to the fact that we are changing our rotation. That change in angular momentum allows it to move away from us, and eventually will slow us down. So much so that we'll lose them. Everybody look at the movie. Right? Okay. And that's a very interesting story when we want to talk about the hypothesis about Venus's two moons. Right? That's a future topic. Okay. Wow, that was a huge tangent for no reason. Anyway, it's just something weird. Core go fast. Exterior goes slow. Okay. So that. Sometimes when you yap, you have to remember that you said everything that's in. Okay. Oh, wait, was this not sharing the whole time?
You gotta be fucking kidding me. Well, this might be fucked.
But it won't work. Like, sure, does anyone watch it? Yeah. I'm gonna really make sure we got.
We gotta start over.
Yeah, not yeah, you will start all the way over. Okay, so
This is how it works. Iron's a conductor. Conductors are great, right? Because they flux freeze. So these moving conductors drag the magnetic lines with them and vice versa. Right? I talked about the fact that rubber bands are in the magnetic field. Magnetic field are the rubber bands in the physics world. And what you're basically doing is as you pull on a magnetic field line, it wants to restore itself. So as the spinning conductor is going, you just are generating magnetic field because it's like, what the fuck? So you have this torsional effect, right? That is generating these magnetic fields. So here's a magnetic field wrapped around the rotating conductor, and then the boundaries here are the locations where it comes out of the diode. Right? So if you think about it like in the context of your bar magnet, right? Bar magnet has polarization, has elements like that. Now these are all minerals that are frozen in. That's not at all what this is. But if you wrap a wire all the way around, like solenoid, and then you draw a current, remember that current's only going one direction through the entire solenoid. Which direction is the magnetic field in the middle? That way. Okay. It's like this. And so it's the same direction, and it flips around, and you go to the other direction. It's an oscillating, self-regenerating magnetic field, follows the core's rotation. The cool thing is that it flips. We see in the C4, I should have shown this, because this is gorgeous.
Where's mine?
When you see these pictures of the seafloor, these are layers, right? They come out and then they freeze, and then they come out and they freeze. And what's really cool about them is that we can see the material being deposited. So amazingly enough, if you look at the center, let's say I'm a really good drawer, okay? And that's the Midlands Bridge. Okay? If you have something that's magma and you freeze it, you lock into place the orientation with respect to the existing magnetic field. So right here, you have all of these dipoles that are up for the purposes of this argument. Okay? Here's the equator, and these ones are bigger, these ones are 0, these ones are south, and these ones are bigger. Good, right? And what we see in the oceanic record, you go a few kilometers this way, okay, then we see the opposite. We see down, and we see big down here, right? We see 0 here, and we see up. We see all of these rocks from millions of years ago have the different polarity. And then you keep going, and about equal distance away, they switch again, back up. So we have geologic evidence for the fact that the diamond flips. And it's frozen in the crust. Isn't that cool? So when we talk about, for example, Mars's crust magnetic field, that's sort of the similar thing. Where it's as the crust was freezing, it's holding on to the fact that there probably was maybe a diamond. Okay. So this is, I'm going to put a star here. We don't know if this is true. As I mentioned, Joe O'Rourke says that basically, he just told me, the idea that Venus moves too slow is a very Earth-centric view. Because what does the word too slow mean to a planet? The question really is about differential rotation and how strong is that differential rotation, given the fact that you need convection. So while to our eyes, one rotation every 200, 300 days may not be enough, right? Because we don't think of that as rapid. That may not be the case for Venus. And so he has models in which you can simulate there being a dynamo today, that slow of a rotation. That's fucking weird, in my opinion. That's something that doesn't feel comfortable to me. But keep an eye on this in the next 30, 50 years. Because we may find that the dynamo just shut off, or maybe that there is a weak dynamo, right? Okay. There's no evidence from magnetic field data currently that there is dynamo. There could potentially be magnetic evidence, right? Okay. Fuck. All right, we're out of time. You know what this is? Switch. Bench, do you see the face?
Yeah.
This is an alien structure. Just pretending like you guys finally are high enough in the ranks that you get to learn about aliens. All right, now we're going to talk about. I'm going to delete this anyway. So, this is a real object. This is called the face on Mars, but it's from Mars Global Surveyor, and it's a rock. It's mountain. But that's fine. Mars is similar. Mars is different from Mars. And we'll talk a little bit about at the beginning of the next class. We'll talk about water, earth, life, and ice. In the context of like where did it get its ice, where did it get its water, and we'll talk about Mars, life, earth, water, ice, because I think these are very important in the context of planetary evolution. You start with something that's molten. You add to it volatiles. And as we'll discuss, one of the primary reasons why we think Venus is such a shit show is because there is no water. So there's some evidence to suggest that plate tectonics and the recycling of crust permits carbon to be sequestered below the surface and therefore avoids the greenhouse effect, right? So our greenhouse effect is self-regulating, as you may be aware, unless we fuck it up with human contributions. But usually we sequester carbon dioxide, stick it back under the surface, and it melts, right? And you can put it into stuff. That's really great. Venus may have had liquid water on its surface and may have lost it. And in the process of losing it, you have that brittle crust and you have no subduction zones, you have no way of recycling that carbon back in, and then you have a runaway greenhouse effect. So let's say you start to lose your water one way or another, that can be fatal. Okay, cool.